Hi guys, welcome to this session on theory of interest rates. So previously we looked at accumulation, we also looked at discount and the present values. In our initial class, we also looked at the calculations involving these three aspects. And we also talked about the cash flow. So this is just like a summary of what we did so far. So we were also talking about considering investments in which capital and interest are paid at the end of a fixed term, and are there being no intermediate interest or capital payments. So that in that instance we're talking about simple cash flows. So that it was just an example of a simple cash flow. Then we also looked at some examples where we're talking about short-term deposit, for instance, in which the lender invests, let's say, a 1,000 and receives a return of 1,035 kwacha in 6 months later. So that 1,000 may be considered to be a repayment of capital, and the 35 kwacha a payment of interest. So what are we saying here? The reward for the use of the capital for 6 months. So in 6 months after using the capital, the lender receives a 35 kwacha as a payment of interest. So we also discussed about the compound and the simple interest rates, and where we had the formulas for the simple interest rate. For the simple interest rate, we talked about C1 plus IN, and where I is the rate per unit time. And we also looked at the compound interest rate. Under the compound interest rate, we had what? C1 plus I to the power n, 1 plus I to the power n. So these are just simple formulas where you need to apply. And we also discussed about the principle of consistency and the discount, and we looked at some examples. So today we are going to look at the nominal rates of interest. So today we are looking at the nominal rates of interest. So under the nominal rates of interest, we consider transactions of the length of time h, or length of time h units, and this h should be greater than 0 and need not be an integer. So here we define I subscript h, which is just what? This is just the nominal rate of interest per unit time on transactions of the term h, and where h is greater than 0. So from the beginning at time t, the effective rate of interest for the period of length h being at the time t is h, then you multiply by I t, then t. So therefore, if the sum of c is invested at time t for a term of h, the sum to be received at time t plus h is defined as, so you get c 1 plus hi h small then t, and then this h, as we said, this h is just the effective rate of interest for the period of length h beginning at time t. So this one we'll call it as equation 1. And then if h is equal to 1, then the nominal rate of interest coincides with the effective rate of interest for a period t is equal to 1. So if h is equal to 1, if you put 1 here, we have what? We remain with I. Then our t is what? Is 1. So this will give us IT. So this simply means that if h is equal to 1, the nominal rate of interest coincides with the effective rate of interest for the period t is equal to 1. And this equation, we call it as equation 2. So in many practical applications, we'll see that I subscript t does not depend on t. So in which case we may write it as if I subscript t does not depend, if it does not depend on t, then we write it as follows. So we have I subscript t will just be equal to I subscript h for all t, and this will be equation 3. So in the previous session, I gave you an example, if you can remember. So this example or a question, that was the last question I gave you, and it was your homework. So the question was saying if the nominal rate of interest is 12% per annum on transactions of a term a month, calculate the accumulation of 100 kwacha invested at this rate after 1 month. So the question was saying if the nominal rate of interest is what? Is 12% per annum on transactions of term a month. Calculate the accumulation of 100 kwacha invested. So this is invested at this rate after 1 month. So here, what are we supposed to do? So we have what? We have h, which is equal to what? 1 over 12. And we also have I, 1 over 12. T is equal to 12%. And this 12% is what? Per annum. That's what the question is saying. So what are we supposed to do here? The effective rate monthly is therefore 1%, and the accumulation of 100 kwacha invested over 1 month is then. So how do we find the effective monthly rate? So we have 100 kwacha. Applying the formula, we have 1 plus 1%, and this will give us how much? This will give us 101. So this is how you do this question. Then so we continue. So if in this case we also have h as what? So in this case, if we have h is equal to 1 over p, where p is a positive integer, so p is positive, p is greater than 0, where and h is the simple fraction of a time unit. It is more usual to write as, how do we write this, as I to the power p rather than I1 over p. So I to the power p is just simply saying I subscript 1 over p. And this we call it as what? Equation 4. So it follows that a unit invested for a period of length 1 over p will produce a return of what? What return will it produce? So this will produce a return of 1 plus ip over p. So here we see that I the power p is simply but nothing as the nominal rate. So this is the nominal. It's a nominal rate of interest. Nominal rate of interest per unit time. And it's also payable, where it is payable P3, or it's payable convertibly. So it's convertible P3 or with P3 rests. So we will have in some questions involving the nominal rate, the question may talk about payable P3 or convertible or monthly. So let's look at an example. So if we have I 1 over 12 is equal to I 12, which is equal to 12%, is the yearly rate of nominal interest converted monthly, such that the effective rate of interest denoted by I is what? 12%. Divide this by 12 and you get as 1% per month. So here we have our effective rate of interest, and which is 1% per month. Now nominal rates of interest are often quoted in practice, but it is important to realize that these do not be converted to effective rates to be used in calculations. So in this example, we're just converting this to the effective rate of interest per month. Now let's look at another example. So this is EG2. In the second example, we say that the nominal rates of interest, the nominal rates of interest per annum quoted in the financial press for local authority deposits on a particular day are as follows. So on a particular day we have what? The term, then we have the nominal rate of interest. So the nominal rate of interest denoted by the percentage. So here we have, which term do we have? So terms are, we have 1 day, then we have 2 days, then we have 7 days, we have 1 month, and then lastly we have what? 3 months. And then the nominal rate, we have 11.75, we have 11.625, then we have 11.5, we have 11.375, and lastly we have 11.25. So the question now says we need to find what? We need to find the accumulation. We need to find the accumulation of an investment at this time of 1000 kwacha for, so A we have what? For 1 week, and B for 1 month. So how do we go about this example? So to express the information in terms of our notation that we have just looked at previously, we need to what? We need to draw up the following table in which the unit of time is 1 year and the particular time is taken as what? As t subscript 0. So we need to form up a table, and then we have the term h, then I subscript h, then t0. So for 1 day, and we're talking about what? In a year. So for a day you divide that by 365, then for 2 days be 2 divided by what? 365. Then for 7 days it will be what? 7 divided by 365 days. And then for 1 month to be 1 divided by 12, since 12 is equal to 1 year. Then for 3 months it will be 3 divided by 12. So here for our IH we get as what? We get 0.1175. Then here we get 0.11625. Then for this one we get 7 days we get 0.115. Then for the year, for the month you get 0.11375, and lastly we get 0.1125 for 3/12. So the first part of the question says we need to find the accumulation of an investment at this time of a 1000 kwacha for 1 week. So for 1 week, what do you have? You have 1000, then 1 plus 7/365. You multiply this by 0.115, and this gives us what? This gives us 1002.21. Then for B we have a 1000, and we need to know for a month. A month is 12, so 1/12, multiply this by 0.11375, and this 0.11375 is coming from here, because we're talking about 1 month, and the month is 1 by 12. 12 is 1 year. So what do we get here? Here we get 1,009.48. So this is how we apply the nominal rates of interest to find the accumulation of an investment. So we note that the nominal rates of interest for different terms are liable to vary from day to day. So here we should not be it should not be assumed to be fixed. So if they are consistent with time and equal, then an investment of, let's say, if we have an investment of maybe 1 million, if we have an investment of 1 million for 2 successive day 1 periods, then how do we find the accumulation? So the accumulation will be 1 million, then we multiply this by 1 plus 0.1175 by what? 1/365. Okay, so here we're talking about in this instance, if you invest if you have a 1 million for a 2 consecutive 1 day periods. Here we're talking about what? Two successive 1 day periods. So here the key is 2 successive, so you have to square this. So this will give us what? This will give us 1,644,000 kwacha. Whereas if we invest a single 2-day term, is it going to give us the same? So for this instance, for the first one, is a 2 successive 1 day periods. What about in the 2 single, if we have an investment for a single 2 day period, for a single 2 day term? So using the same 1 million, how are we going to get? So for a 1 million, we have what? 1 plus 0.11625, then this by 2 days, 365. So since this is not a 2 successive 1 day period, we are not going to square this. So what do we get here? So here we get 1,637 kwacha. So this apparently is inconsistent, and by the fact that the market expects interest rates to change in future. So these ideas are related to the term structure of interest, which we'll see later on. So this is just an illustration, so we can see that this and this are slightly different but almost similar. Now let's look at accumulation factors. So we look at accumulation factors. And we use these concepts to apply them to the force of interest. So let's look at, if we consider investments which are made in order to exploit the growth of money under the action of compound interest as time goes forward. So in order to quantify this growth, here we introduce the concept of accumulation factors. So here we let the time to be measured in suitable units. So let's say years, and then for a time of 1 is less than or greater than a time of 2, we define a t1 t2 to be the accumulation at time 2 of a unit investment made at time 1 for a term of t2 minus t1. So here it follows by the definition of the I subscript h, that for O t and h is greater than 0, the accumulation over a time of length h. The time of length h is what? It's nothing but a t comma t plus h, which is nothing but 1 plus h I, and then subscript h and t. And there we can work out IH. So what is our IH? IHT. So how do we get IHT? IHT is nothing but a t comma t plus h minus 1, everything over h. So here the quantity that we called a t1 comma t2 is nothing but the accumulation factor. It's nothing but the accumulation factor, since the accumulation is at time t2 of an investment of sum c at time t1. So here, if we want to find the accumulation of an investment at time t2 of an investment of some c1, we get it as ca, and then t2 t1 comma t2, right? So if we talk about the principle of consistency, then in relation to this accumulation, what do we have? So under the principle of consistency, so what do we get here? Under the principle of consistency, we have t naught comma t1 comma t2 is nothing but a t naught comma t1 and a from t1 comma t2. So under this, it follows that we have this consistency t naught is less or equal to t1 is less or equal to t2. Now let's look at an example. So an example says, what does it say under this? So let's look at an example. An example says let time be measured. If you let time be measured in years and suppose that for all t1 is less than t2, less or equal to t2, what do we have? We have this function a t1 comma t2 is equal to the exponent of what? 0.05, then t2 minus t1. So what are we supposed to do here? Here we are supposed to verify that the principle of consistency holds and find the accumulation and find the accumulation 15 years later on an investment of 600 kwacha made at any time. So that's how we're supposed to do this one. So here we have to consider what? So we consider under the principle of consistency, T1 is less or equal to, let's say, S less or equal to T2. And then we have what? Our accumulation as T1 comma T2, which is nothing but A T1 comma S and multiply this by A S comma T2. So the right hand side of this expression, and we can write it as what? So the RHS, under the RHS we have the exponent. From the question, what do we have? We have this one. So from considering the RHS, we have 0.05, then S minus T1. Why are we writing S minus T1? Because under the principle of consistency, our S is less than, our S is greater than T1, this one here. Then you multiply this by another exponent. Since we're dealing with the right hand side, 0.05. Then what do you get? T2 minus S. So let's put these together. If we simplify the right hand side, what's common? The exponent. Then open bracket, we have 0.05, it's common. Then T2 minus T1. Yes. So if you open these brackets, what do you get? If you further simplify this, this brings you back to A, T1 comma T2. So this is equal to now the LHS. So now we have proved that the right hand side of the equation is equal to the left hand side. Then we also need to what? We need to find the accumulation 15 years later of an investment of 600 kwacha. So for 15 years, how do we do this? For 15 years, for 15 years. So what is our time period? Our time period here is 15 years, and we have from the question we have what? 80 we get from this expression here. So we have what? We have 600, and then you multiply this by the accumulation. In our question, our accumulation was given by this expression. So we have e to the power 0.05 by 15. This gives us our accumulation after 15 years as 1,270.20 kwacha. So this is how we apply the accumulation factor to find the accumulation of 600 kwacha after 15 years. So we now let's look at the force of interest. So we move on to the force of interest. The force of interest. So under the force of interest, we have to define some terms, and we looked at the accumulation factor, which is nothing but a, and then t comma t plus h, which I've looked at in the previous scenarios. So here, in general, of course, the limiting value will also depend on t. So here we therefore assume that for each value of t, there is a number. So each value of t, there is a number delta t such that the limit as h tends to 0 plus I h t is nothing but equal to the delta t. And here we have seen this notation. This notation just indicates that the limit is considered as h tends to 0. Okay, and considering only positive values, so that's why we have 0 plus. This 0 plus only indicates that we are only considering positive values. So it is usual to call the delta t, this one, we have this delta t. So delta t, we call it as what? This is nothing but the force of interest, per unit time, and this unit time is at time, per unit time at time t. So in view so under the nominal rates of interest per unit time at time t, convertible momently. So how do we now incorporate the delta t, which is the force of interest, with the accumulation? So we may define delta t nothing but, in terms of the accumulation factor, it's nothing but the limit as h tends to 0 plus, then we have the accumulation factor as a, t comma t plus h minus 1, nothing but everything over h. So the force of interest here, which is what? Delta t, is defined in terms of the accumulation function, which is what? Which is nothing but a t1 comma t2. So this is the accumulation function which we looked at. And but when the principle of consistency holds, it is possible under very general conditions to express the accumulation factor in terms of the force of interest. So what are we talking about? So an important formula under the force of interest in terms of the accumulation. So if the force of interest delta t and the accumulation function, which is given by a t naught comma t, continuous functions for t and for t greater or equal to t naught, and the principle of consistency holds, and this principle of consistency holds for t naught is less or equal to t1 less or equal to t2, Then we can say that the accumulation of t1 comma t2 is nothing but the exponent of the integral from t1 to t2. Then we have the force of interest delta t dt. Yeah. So under this, we can also we can now let's look at some example. Um, let's look at some example. So an example can say the force of interest per unit time. So I'll take this example. So the force of interest per unit time is nothing but 0.12 per annum for all t. So the question is, find the nominal rate of interest per annum on deposits of terms. So find the nominal rate of interest per annum on deposits of term, so 7 days, and B, we have 1 month, and C, we have what, 6 months. So let me read the question again. The force of interest per unit time delta t is equal to 0.12 per annum for OT. Find the nominal rate of interest per annum on deposits of the first part 7 days, second part 1 month, and the last part 6 months. So how do we do this? So we note that the nature of time scale here is what? We are using year. And we have, what do we have? We have delta t is nothing but 0.12 for OT. So we have now what? And here the question is talking about the nominal rate of interest. We need to find the nominal rate of interest per annum, and the nominal rate of interest was denoted by what? IH, which is nothing but IH, and T, which is nothing but the exponent of the force of interest, which is what? 0.12 h minus 1 everything over h. So in the first part we are saying what? For 7 days. So how do we find h is equal to 7 over 365? And for B, we have our h is equal to 1 over 12, and C, our h is 6 over 12. So from here, it's very simple to now obtain the nominal rates of interest. Simply replace I, H, T, where in the first instant, we have the exponent of 12, 0.12, and our H is 7 over 365, minus 1, everything over 7 divided by 365. So I'll leave you guys to find out the answers to this for part A, B, and C. So we will further discuss the rest of the questions in our next session. So thank you so much and have a pleasant day.